Hello, welcome to this video. Today we're going to prove Euler's expansion to Fermat's little theorem. So first of all, let's look at what Fermat's little theorem actually says. So it says for P being prime, A being a natural number, and P not dividing A, if those three things hold, then we can say that A to the P minus 1 is congruent to 1 mod P. So this is Fermat's little theorem. Now Euler's expansion to this theorem is if A and N are natural numbers and A is co-prime to N and N are co-prime. Basically, the GCD, the greatest common divisor between A and N, is 1. If those two things hold, we can say that A to the phi of N is congruent to 1 mod N. But what is phi of N? Well, phi of N is the amount of numbers not bigger than N and co-prime to N. In natural numbers, of course. So for example, phi of 3, how many numbers are not bigger than 3 and co-prime to 3? That's 2. 1 and 2. What is phi of 15? How many numbers are not bigger than 15 and co-prime to 15? I'm not going to write all the numbers, but the answer is 8. So for any natural number, of course, there is phi of n. For any natural numbers, there's phi of n. If we raise a number that is co-prime to n to the power of the amount of things co-prime to n and not bigger than n, that will be congruent to 1 mod n. So that is our goal, to prove this second theorem. So let's begin. So the first thing we want to do is define a set, which is S, and we will call it, and the definition of this set S is all the numbers that are not bigger than n and co-prime to n. So it's going to be, we'll call it x1, x2, all the way on to x phi of n, because we know there are phi of n of them. And our goal is to find another set that is not immediately like our set S, so it's not the same definition of S, but we'll be able to show that it's the same as S. So our goal is to find a set with phi of n elements in it. Each one of those elements is not bigger than n, and each one of those elements is different to another element that's in a different place, and each element is co-prime to n, because that is basically the definition of S. We find the amount, the elements in T are all different. They're all not bigger than n. They're all co-prime to n, and because the amount of them is the same as the amount as phi of n, we'll be able to say they're all they're all of those numbers not bigger than n and co-prime to n. So basically, we'll be able to show t is equal to s. But we're getting ahead of ourselves, so let's try to form a set like this. So we will define a new set, s prime, which is basically each number in s multiplied by a, because we know a and n are co-prime, and each one of those is co-prime to n. A times each one of those will still be co-prime to n. So this will be ax1, ax2, so on until ax phi of n. But now we lost the fact that all of those should be not bigger than n. So that's very simple to fix. All we do is do mod n to each one of them. So we will define t to be ax1 mod n, then ax2 mod n, ax3 mod n, so on until ax phi n mod n. So that's all of those mod n. And this is the set we're looking for. Now that's all we need to show. There are phi of n elements in it. And that's not automatically obvious, because for that we need for different places in t. So in place I and place j, as long as I and j are different, axi mod n and axj mod n will be different. So any two elements from different places will be different, and so there won't be something like 2, 2, 3 that by definition of a set is actually just 2, 3 and only contains two elements. So we're gonna show that, which will give us phi of n elements, and that all of those are different. And then we're gonna show, and that we obviously automatically get, just by the definition of mod n, all of those are not bigger than n. And then we will show, that all of those are co-prime to n. So let's begin. So to show that each two in different places are different, we will look at, we will assume that there are I and j that are places which contain this the same element. The element has the same value, and then we will show that it actually means they are the same place. Okay, so let's begin. If axi mod n is equal to axj mod n, we will show that that implies that I is equal to j. So if we find two elements that are equal here, that means they'll have to be in the exact same place, meaning, which will give us that any elements in two different places will have to be different. So axi mod n is equal to axj mod n. That means that if we subtract axj, that will give us that axi minus axj. Well, if those are the same mod n, that means that this will be congruent to 0 mod n. Basically, n divides this. And so we can take a out of this, subtraction, and we'll get we'll get that n divides a times xi minus xj. But now, because a and n are co-prime, if n divides this, that means that all the things in n have to go here, in this product. but A and N are co-prime, so they can't go into A, which means that N will have to divide xi minus xj. So xi minus n divides xi minus xj. But now this is between 0 and n. This is between 0 and n. So this is between 0 and no. This is between 1 and n. This is between 1 and n. So this minus this is between 0 and n minus 1. And because this is between 0 and n minus 1, but n still divides this, this has to be 0. Because n doesn't divide any natural number smaller than it. And so from this, xi minus xj is equal to 0, meaning that xi is equal to xj. But if xi is equal to xj, by the definition of S, I has to equal to j. Because if I was different than j, xi would be different to xj, they would be in different spots in S. So that means that I is equal to j. And that finishes off the first thing we want to prove. Any two different places hold different elements, meaning that there are phi of n different elements in T. Now let's show, we already know they're all not bigger than n. Now we will show they're all co-prime to n. Okay, all is left to show that each element in T is co-prime to n. So what we will do is assume there is a number, a natural number d, that divides an element in here and n. Then we will show that that number has to be 1, meaning that which by the definition of coprime will give us that any element in T is coprime to n. So if D divides AXI mod n, and at the same time D divides n, well, that means that we can basically add on multiples of D until we reach AXI. That's pretty much the thought behind this. So D divides AXI mod n and D divides n. So we can basically add multiples of D onto AXI mod n until we get AXI. And so we can say D divides AXI and D divides n. But now let's assume that D is not equal to 1. If D is not equal to 1 and D divides n, because A and n are co-prime and xi and n are co-prime for all I, that means that D does not divide A and D does not divide xi. In fact, not only does it not divide, they're co-prime. So let's actually rewrite this. So the GCD of D and A is equal to 1, and the GCD of D and xi is equal to 1. Because if it wasn't 1, and it was something bigger than 1, we would have found something that divides n, because it would have divided D, and something that divided either A or xi, and it would be bigger than 1, which would contradict that xi and n are co-prime, and that A and n are co-prime. But if D is co-prime to A and to xi, D is co-prime to AXI, meaning that D and AXI are co-prime. So their GCD is 1. But because D is not 1 and D is not 1, we can say that D actually does not divide AXI. Again, really just by the definition of coprime, or something that really comes straight from the definition. And so if D does not divide A times XI, but here we know that D does divide AXI, we get a contradiction. Meaning that D, it cannot be the case that D is not 1. But because D is a natural number, if it's not 1, that means D is 1. Meaning that if there, and so, like I said, if there is a natural number that divides both of those, that number has to be 1. Meaning that these are coprime for all I. So that's what we wanted to show. Any two elements in different places in T are different. Obviously, all of them are not bigger than n. There's phi of n elements in T, different elements in T, and each element is coprime to n. But because there's phi of n elements in T, and they're all coprime to n and not bigger than n, and they're all different, that means that these are actually all the numbers, and not some of them, but all the numbers that are not bigger than n and coprime to n, and obviously all different. Meaning that T is equal to S. But if all the elements of T and S, if all the elements of T and S are the same, not necessarily in the same order, but overall they're the same, that means that the product of the elements in S and the product of the elements in T is also the same. So x1 times x2 on and on until x phi of n is equal to ax1 times ax2 all the way to ax phi of n, all of this mod n, which is a to the we're multiplying a by phi of n times, and so this is a to the power of phi n times x1 times x2 on and on until x phi of n. And let's cut the line here. Mod n. Meaning that because for x1, x2 up until x phi of n, they're all coprime to n by definition, which means one of the properties of coprime is the product of coprimes is still coprime. The product of numbers coprime to another number is still coprime to that number. So all of this is coprime to n, and this is coprime to n. If they're coprime to n, another property of coprime, we can cancel them out in this mod n, sort of the inverse in mod. Of course, there is no n. Of course, there's not always an inverse in mod, but this is sort of dividing by this because it's coprime to n. We can do that, meaning that 1 is equal to a to the phi of n mod n, which means a to the phi of n mod n is 1, meaning that a to the phi of n is congruent to 1 mod n. And that finishes off our proof. And before I go, there's a reason this is called the expansion Fermat's theorem. Obviously, this expands from prime numbers to all natural numbers, and you can also automatically get Fermat's theorem from Euler's expansion to Fermat's theorem. If n is a prime number, how many numbers are co-prime to a prime number and are not bigger than that number? Well, 1 to p minus 1, where p is your prime number, and so phi of p, where p is prime, is p minus 1, and a and p being co-prime is the same as p not dividing a, because p is prime. So this automatically gives this, which is why it's called the expansion of Fermat's theorem, because it does give you the case where p is prime, but it generalizes to all the natural numbers. That's it. If you want more content like this, please subscribe to my channel. I'll be uploading more just interesting problems and things like this in the future. And finally, that's it.